Dear colleagues, my name is Charlie Hum, and I'm welcoming you to today's presentation, in which we will discuss how we can bring the code to bedside on the example of prostate cancer. And I especially want to thank Professor Hosten for the invitation to contribute to this great series of presentations on the topic of AI in the field of radiology. In the next slides, I want to give you some background on prostate cancer and the use of multiparametric MRI. And then we dive into radiomics and deep learning. And in the end, I want to give you some information and insights into our project, which we are conducting in cooperation with the Charité. The prostate is rather one of the smaller organs of the human body. However, prostate cancer is one of the major health problems. Prostate cancer is the most common cancer in men in the Western world, as you can see on this map. And we radiologists play a crucial role in the early detection and classification of prostatic lesions which are suspicious for prostate cancer, especially by using the PIRATES protocol, which enables a standardized diagnosis and reporting of these lesions. In this protocol, three typical sequences are suggested to use: the T2, the DCE, the dynamic contrast enhanced sequence, and also a diffusion weighted imaging sequence, which also includes a ADC map. All these different sequences provide also different information, such as information on the anatomy, perfusion, and cell density of the lesion. When we can look at these lesions, we can see a prostate cancer lesion right in the upper right part of the prostate. And in this case, we might think, well, that's an easy part, because if prostate cancer glows as a bulb on this sequence, we should be able to do those tests. Unfortunately, we only achieve a moderate inter-reader reproducibility shown in recent studies. This leads us to the unmet clinical need for an improved diagnostic accuracy and an improved workflow efficiency. With this in mind, we get to our next point with the title, Radiomics and Deep Learning, the New Hope. In preparation for this talk, I found a very interesting study in which those authors looked into the main keywords in emerging technologies in cancer research. And when we look into this table on the left-hand side, we can see that in this table, the 10 top co-occurring key features are listed, which emerge together in emerging technologies and cancer research. And 4 of those 10 are classification, machine learning, prostate cancer, and feature selection, which shows that prostate cancer and AI deep learning is a major topic in emerging technologies in cancer research. This is also reflected in several studies. Among some, we can find review articles in well-known journals such as Nature, but also several other studies in typical radiological journals, but also other fields. Not only radiologists benefit from these new trends of emerging technologies, such as pathologists, which was shown in a recent study in The Lancet, where a deep learning system was trained for the classification of prostate cancer on histological slides. Back to radiology. And when we start with our first topic in specifics with radiomics and deep learning, we want to look into radiomics and the quantitative image analyses. In a typical workflow, we can see that we have a basic data set, imaging data set, in our case, the multiparametric MRI, which can be supported by clinical or genetic information. Then we get to our post-processing step, where we segment the lesion, the organ. Then we extract imaging features or radiomic features which are of interest to us. And finally, by using also a machine learning algorithm, we select those features which correlate to our classification. Finally, this approach might help us in an improved classification and risk stratification, and finally might help us in the overall diagnostic task. When we remember back to the slide, we can see the 3 sequences which are suggested by the PIRATES protocol, the T2, the DCE, and the DBI. But you might think, well, we have 3 sequences, we should have plenty of information to get those diagnoses straight. However, when we look at the different anatomic zones in the prostate, the transition zone and the peripheral zone, we can see that only one sequence is really relevant for each of these anatomic zones. In the T2, we only look at, in the transition zone, we only look at the T2 sequence, while in the peripheral zone, DVI. So when we look in the Pirates protocol, we can see that actually only for each anatomic zone, we only look at one sequence, as in all the others, it just says any. And when we think back, we only achieve a moderate inter-reader reproducibility, and we only use one of potential three sequences, which brings us to the task, okay, let's extract more imaging features by using radiomics. And several studies have tried to do that, with the typical conclusion that especially the ADC is relevant for an improved diagnosis of prostate cancer, which is also supported in several other studies. And we might think, well, we have our answer. The DVE, or the diffusion-weighted images, are the most relevant. Unfortunately, there are also studies which show the opposite. In this study, for example, the 10 best performing radiomic features with a result significant in the performance compared to Pirates reporting, we can see that 7 out of those features were T2 weighted imaging features, while only 3 were based on diffusion weighted imaging. As this is not enough, we also have different studies which claim that these algorithms should be trained zone specific, so for each anatomic zone individually. And also a study published in Radiology by Dr. Bonekamp showed that ADC radiomics algorithm doesn't outperform just a regular ADC mean calculation. So this also brought into question what is the actual value of radiomics. So finally, instead of answering the problem or solving the problem, we are rather confused by these different and divergent study results. And especially studies showed that the results of these radiomic studies is not really translatable or transferable to other data sets, other institutions, and other studies, and are not really reproducible. So we are left with our unmet clinical need of improved diagnostic accuracy, again, by ourselves. So from here, we jump into deep learning, which might be a next step in the development of these emerging technologies. And I want to discuss the deep learning approach with the topic from code to bedside. We all have in mind the typical workflow of a deep learning study. So we have the input data on the left-hand side, our deep learning system in the middle, and on the right-hand side, our tasks, so classification or prediction. The approach of deep learning system was applied by several researchers and teams and has achieved great performances with AUCs of over 0.9, which also led to high impact studies such as publications in radiology or European radiology. But when we do the real literature check and the check of clinical applicable tools, we can see that the deep learning system made it to PubMed. Unfortunately, it didn't make it to clinical care or patient care. So the question is, how do we bring the code from PubMed to patient care? We believe that the black box design is a major limitation to the clinical translation, as the black box design is a word for the description that deep learning systems might outperform radiologists in a certain task. However, they are not able to display their decision-making and justify their decisions. So it will be difficult for clinicians to just accept the deep learning system, which is supposedly better in the task than the radiologist or the clinician themselves. The deep learning system and the black box design is also connected with doubts in ethical and legal aspects, which are, in our belief, one of the major barriers to a clinical translation of these deep learning systems. So, in order to overcome the black box design, we started to develop explainable deep learning systems, and we started with a study at the Yale University, where we trained an explainable deep learning system for the differentiation of focal liver tumors on multiparametric MRI. In this study, we used 6 different types of lesions, 3 benign lesions, so cysts, hemangiomas, and focal nodular hyperplasia, and 3 malignant lesions, including the hepatocellular carcinoma, the intrahepatic cholangiocarcinoma, and the colorectal metastases. In total, we included 494 focal liver lesions, and finally trained a deep learning system with 3 convolutional neural network layers, 2 maximum pooling layers, and 2 fully connected layers, with the task to differentiate among those 6 classes. In a second step, we then approached the interpretable aspect of the deep learning system with a post-hoc probabilistic approach by assigning 14 imaging features. All imaging features were supported by 20 example lesions, and then investigate the relevance of these imaging features in the decision tool or decision tree of the deep learning system by finally performing an output in which deep learning demonstrates up to 3 imaging features being relevant for the classification. Finally, we were able to achieve a very good accuracy in the classification tasks. So with an accuracy of roughly 92% and an AUC of 0.99. We also performed a reader study in which the deep learning system outperformed 2 radiologists in the diagnosis of these focal liver lesions. And in the second step, we were then also able to extract those imaging features which were relevant for the classification, such as here in the example of cholangiocarcinoma. We can see that the imaging feature progressive hyperenhancement, nodularity, and heterogeneous lesion were the 3 most important imaging features for this classification. This is also demonstrated in this image, where we can see that the heat map indicates where those imaging features were observed in the MRI dataset, which correlate to the lesion themselves. And in addition, we assigned a relevance score, which reflects the relevance of these imaging features for the classification or decision-making of the deep learning system. With this as a basis, we started to translate this approach to prostate evaluation on MRI, and we defined 3 goals. First, we wanted to curate a large RADPAS correlated data set for the development of a deep learning system. Second, we wanted to develop and validate a 3-dimensional interpretable deep learning system. And then thirdly, we wanted to apply the previously developed system to design a clinically applicable tool and software which can be then used in clinical routine. We first designed a custom interface for the annotation task and the curation of the data set, where we can see registered MRI sequences with the T2, diffusion-weighted images, the ADC, and the DCE, and a lesion identification tool for the demarcation of the lesion. And on the right-hand side, we can see the RADPAS correlation and radiological report, which is blinded here. But also we can see the biopsy takings with the several cylinders with either the Gleason score or just tumor-free tissue. And finally, we were able also to assign specific imaging features for each lesion we identified. Finally, we performed an internal review to also achieve a high standard of data quality. And finally, with this approach, we were able to create a data set with 1,136 consecutive biopsy-naive men, in which we assigned or identified 3,186 prostatic lesions, in which roughly 1,000 lesions were prostate cancer and the remaining lesions were benign lesions, in which we also included benign prostatic hyperplasia, so nodules in the transition zone, and also prostatitis, which are both typical differential diagnosis of prostate cancer and sometimes ambiguous for a radiologist to clearly define them as benign. We then use the typical workflow of deep learning. On the left-hand side, we have our input data, so the MRI sequences, the convolutional neural network, and on the right-hand side, our classification tool, in which the deep learning system differentiated lesions between benign prostatic lesions and prostate cancer. Finally, we achieved a very good performance, which we were happy to present at the RSNA last year, with an AUC of 0.9 in differentiating these prostatic lesions. And we also trained a second deep learning system for the differentiation of clinically relevant prostate cancer and clinically insignificant prostate cancer, which is defined by the Gleason score. Unfortunately, in this task, the deep learning system only achieved a moderate performance. So we have room for improvement regarding this task. In the next step, we are now planning to extract the imaging features. We assigned PIRATES imaging features, all in line with the PIRATES protocol, and with the goal finally to have the classification in benign or malignant, with an addition of the PIRATES score, which supports the classification and gives some insight into the decision-making of the deep learning system, so the radiologist can actually try to reason why the deep learning system got to its conclusion. Finally, we want to perform again a reader study, as we did in our liver study, and then to develop the applicable, clinically applicable tool to actually bring the code to patient care. Obviously, the deep learning system has potential also in other fields of prostate diagnosis, such as response assessment after focal therapies, but this is some kind of perspective for the future. Thank you so much for your attention. I hope you are now interested in prostate cancer and prostate cancer diagnosis. And I thank you for your attention, and bye-bye.